Yes, I'm ready.
Perfect, great. Good afternoon, everybody. Happy Friday, and thanks for joining today's NC-CAV seminar. Today we are delighted to have Dr. Tianjia Yang, who is currently a postdoctoral scholar at Pennsylvania State University. He received his PhD degree in transportation engineering from University of North Carolina at Charlotte, which is a partner of NC-CAV Center. And I believe he was working with Dr. Wei Fan. Am I correct, Dr. Fan?
Yeah, that's right.
Okay, perfect. And Dr. Yang also received his master from Tanji University and bachelor from Haojiang University of Science and Technology. His research interests include intelligent transportation systems, connected and autonomous vehicles, traffic flow theory, machine learning, and operation research. And his today's talk is about the use of deep reinforcement learning approaches for transit signal priority, especially dealing with connected autonomous vehicles. With that, I'm going to passing the stage to Dr. Yang.
Thanks. Now let me share my screen. So, good afternoon, everyone. I'm very glad to have the opportunity to share with my research during my PhD study. So this research was conducted with the advisor of Dr. Wei Fan, and the title is Transit Signal Priority on the Connected Vehicle Environment, Deep Reinforcement Learning Approach. So first of all, I'd like to introduce why I choose this topic. So as a traffic engineer, we all know that congestion is a key issue in transportation, and typically there are two ways to mitigate congestion. One is to construct more infrastructure, and the other is to improve the efficiency of existing infrastructure. And from the figure in the top right, we can see that start from 1960, the infrastructure in terms of public road mileage increased a little, but the demand in terms of vehicle mile travel increased significantly, and so we can see that constructing more infrastructure sometimes is not really a feasible option because the constraints such as limited space and limited money. So I choose to improve the efficiency of existing infrastructure. And among the methods that can address this congestion, the optimization of traffic signal is a classical but important research topic. And also, we know that public transportation system can transport more passengers with the constraint of space, and it's also an affordable and sustainable travel mode. But it is less attractive because if we want to take buses, we have to share spaces with others, and sometimes we have to experience longer waiting time, longer travel times. So there's some strategy named as transit priority have been proposed, which aims at providing higher quality transit services to the public. And it can be classified into two levels: the macroscopic level, which involving formulating policies and providing subsidies to constructing more public transportation systems. And my research is focused on the microscopic level. I try to grant priority to transit vehicles. And the traditional transit single priority strategy generally causes adverse effect to other traffickers because we know that right-of-way is a limited resource, and if we want to grant a priority to transit vehicles, it will sacrifice the right-of-way of other traffics. So this drawback, this limitation limited its widely implementation in the real world. But now with with the technology advancement, especially for the connected vehicle technology, which can provide richer real-time data, and for the artificial intelligence, which well, with that we have the ability to develop smarter single controllers. So it may have great potential to make significant progress in this topic. So my research objective is to develop a multimodal single control framework that use connected vehicle data and deep reinforcement learning approaches to optimize the performance for both transit vehicles and private vehicles. So first of all, let me briefly introduce what is reinforcement learning. If we want to apply reinforcement learning to some problems, first we have to model the problem into a Markovian decision process problem. And this Markovian decision process typically has 5 elements. The first is S, which is a state of all possible states in the environment. So for our problems, the state is what we can perceive during the decision-making process. And the second is the set of possible actions of the agent. And our agent is the signal controllers. And typically there are 2 different actions. One is to decide whether to switch to keep or switch to the next phase when the phase sequence is fixed. And the other is to decide what is the next phase. And the third element is the probability of state transition, and it is an abstract concept. And if we want to use model-based reinforcement learning, we have to model this probability. And the reward is the immediate feedback defined by ourselves. So when the state of the environment transits to the next state, it will give back a reward, and the reward is defined by ourselves to guide the agent to perform what we expect. And the gamma is a discount factor, and it is used to decide how long we want the agent to consider for the future. So for the goal of the reinforcement learning, we want to find a policy that can maximize the cumulative reward for expected cumulative reward. So this is the basic idea about reinforcement learning. And in my research, I use several different reinforcement learning algorithms, like deep Q network. It is a classic deep reinforcement learning algorithm, and it is a value-based algorithm. So for this kind of reinforcement learning, we try to find a value for the state action pairs, and based on those findings, we can decide which action we should take in a given state. And the second deep reinforcement learning algorithm we used in this research is proximal policy optimization, and it is different types of deep reinforcement learning, and it updates the whole policy. And it uses gradient descent method to update the policy, and use a neural network use neural network to represent this policy. So I will not dive into the algorithm details. And for my research, I focus on how to define the state space, the action space, and the reward function to apply those deep reinforcement learning algorithms to solve my problems. So for the state space, because we consider to use the data from the connected vehicle, so first we construct the so-called vehicle-based array, use discrete traffic state encoding methods. And by using this method, we divide the. Let me use some. So we divide the length for each approach into several small cells with predefined length. And if a connected vehicle is located at each decision step, if a vehicle located in each cells, we can obtain their passenger occupancy and speed, and then we fill this information into the corresponding tables. So for this method, we can construct two tables with to record their speed and occupancy, and as well as their position. And for the later research, I also use data fusion technology that define a combined state with both a vehicle-based array and a feature-based vectors. So for vehicle-based array, is just like what we construct in the vehicle-based array, and then we construct a feature-based vector, use the number of queued vehicles in each lane. And in this way, we can address the problems that in low connected vehicle market penetration rate scenarios. And for the action space, we also developed two different action space. The first action space is a simple discrete action space. So for a typical four-leg intersection, it has 8 different phases. So the action set is 8 different actions. And then we introduce a lower action space, which is named as multi-discrete action space. And by using this kind of action space, we can decide the set of we can decide the phase of the next phase, and also the green time of the next phase simultaneously. And by introducing this kind of action space, we can reduce the decision frequency significantly. And for reward function, since we want to provide priority to transit vehicles, we use person delay instead of the simple vehicle delay here. And at each decision step, we obtain all the delay from the connected vehicle, and as well as their passenger occupancy. The passenger occupancy here act as a weight, and times with vehicle delay it can. And times with vehicle delay, then we can calculate the cumulative person delay at each decision step, and the reward is defined as the differences between the sequential decision steps. So by constructing such reward function, we can provide more attention to vehicles that carry more passengers. So typically, buses carry more passengers compared to private vehicles. So there will be grant more attentions, and there will be give more priority. And by using this reward function, we grant not unconditional priority, but conditional priority to vehicles. And to test our proposed framework, we built a test bed using Sumo, and we built an isolated intersection based on the real world data. So this intersection is located at east of Charlotte, and we got the traffic volumes for both peak hour and off-peak hour from Charlotte DOT. And for comparison, we also built 3 different controllers using popular control strategies. The pretend controls, pretend singular controller, activated singular controller, and also activated singular controller consider transit singular priority. For the deep reinforcement learning-based controller, we use deep queue network here to train the agent, and we trained 2 different agents based on different traffic demand. And for the neural network, we use convolutional neural network with 6 layers. And the detection range, here we sent as 350 meters, and the cell length we sent is 7 meters. With just for the private vehicle, it can only occupy one cell. So the input representations is 50 by 16 by 2. And the output is the Q value of 8 actions. And then we choose the actions with the largest Q value. So in this scenario, the buses and the cars are all connected vehicles, and there are also other basic settings. For example, the simulation time is 1 hour with a 10 minutes warm-up period, and for simplicity, we set the passenger occupancy to be a constant value. So it's 30 passengers for buses and 1 passengers for cars, and the bus travel in a north-south direction. This table shows the average delay for these controllers, and we can see that with the controller consider transit single priority, the average bus delay decreased significantly, and by grant unconditional priority, the ATSP controller can have the best performance in terms of average bus delay. But if we consider average person delay, the DQNSC have the best performance in terms of both peak and off-peak hours. And for the off-peak hours, the performance is much better compared to other controller. So, because for off-peak hours, there are much more room for optimizations, in my opinion. And we also conduct sensitivity analysis in terms of market penetration rate, passenger occupancy, and arrival headway. And for market penetration rate, as we expected, with the increase of market penetration rate, the performance for all these vehicles are increased. And we can notice that the 14% is a critical point. Before the 14%, the increase of performance is pronounced compared to after 14%. And for passenger occupancy, with the increase of passenger occupancy for the buses, the average bus delay decreased significantly. And at the same time, the average car delay, which is the light green line, increased just a little. So this is what we expected, because it shows that our controller can provide more priority to buses, but at the same time have less adverse impact on regular cars. And for the arrival headway, it is insignificant here. It is insensitive here. So later we try to address the issues that when the market penetration rate is very low, the performance degrades significantly. So we we develop 4 more deep reinforcement learning based controllers, and also we introduce the combined state space and the multi-discrete action space, try to enhance the robustness of the controller in mixed traffic scenarios. So for this experiment, we just use private cars, and we don't consider transit single priority. And we trained 8 different agents for these 8 controllers with peak and off-peak traffic demand. And for the traffic curve, we can see that they can converge to a stable traffic curve. And for the in terms of average delay, for the basic scenarios, which means that the connected vehicle, it is 100 connected vehicle scenarios, we can notice that with the introduction of multi-discrete action space, the performance of the controller improve significantly compared to the traditional controller and as well as the simple deep reinforcement learning based controller. And then we investigated their performance difference in different market penetration rate scenarios. And as shown in this slide, the PPO-SC-MC, which is use PPO algorithm and with multi-discrete action space and combined state space, it has much stable performance. Or even at when the market penetration rate is as low as 20%. And for the average delay for both connected vehicles and non-connected vehicles, it's outperformed the baseline. And the baseline is the pre-timed controller. And we can see if we don't use the multi-discrete action space and the combined space, their performance at the low market penetration rate is unstable and it's very bad. And after that, we expand our objective to multi-intersection scenarios. So we use multi-agent reinforcement learning to solve that problem. And by applying multi-agent reinforcement learning, we have to model the problem into partially observable and Markovian decision process. It's a bit different. It is a bit different compared with Markovian decision process. It also have a state, but the state is the global state of the environment, and it also have action space. Here, the action space is a joint action space for each agent, and it has an extra element which is local observation. And the local observation is the observation that each agent can observe. So for multi-intersection scenarios, we assign each agent to control each single controller. And the reward is the shared reward that depends on the global state and joint action. And also it has a probability transition probability function. And the gamma is a discount factor, the same as the Markovian decision process. And the goal for this multi-agent reinforcement learning is to learn a joint policy that each agent can map its local observation to action, and at the end of the day, it can find the maximal cumulative shared reward. And we use a training technique named as centralized training and decentralized execution. So because PPO has two components, one is the actor network and the other is a critical network. So we use centralized training. Here we construct a centralized critical network. The input is the global state and the shared reward. And based on the global state and the shared reward, it calculates the Q value for each actor. And based on the Q value and the local observation, each actor updates its own policy. And after training, it can decide their own action based on their local observation. So during execution, it can perform in a decentralized manner. And for that, we defined a global state For the local observation, it is the same as what we defined in the single agent reinforcement learning. And for the global state, we combine the local state of each controller, and then we added the phase state of each agent. To evaluate the performance, we construct two different scenarios, two different test beds. The one is hypothetical corridor with 5 identical intersections. So they have the same layout and they have the same turning movement volumes, and the bus road is east and westbound. And also we built a real-world corridor testbed, and this corridor is based on a corridor located at east of Charlotte. And we also obtained real-world traffic volumes for peak hour and off-peak hour from the Charlotte DOT. And you can see that the 5 intersections are different, and it even have a T-shaped intersection. And we also build different controllers for a fair comparison. For the multi-agent reinforcement learning-based agent, we trained 2 different agents. The first is just simply use multi-agent PPO, and the action space is discrete action space. And then we introduced the multi-discrete action space, and we want to compare the performance in our experiment. And you can see from the training curve, in multi-agent system, the training curve is not as stable as in single-agent environment, because it is multi-agent system is much more complex compared to single-agent system, so their training curve is not stable, especially in real-world scenarios, because their intersection is not identical, and the problem is much more complicated compared to hypothetical scenarios. And this slide shows the statistic of average delay in terms of average bus delay, average car delay, and average person delay. And we can notice that our proposed framework, MA-PPO and MA-PPO with multi-discrete action space, showed superior performance in terms of both these metrics. And we also conducted sensitivity analysis in terms of market penetration rate, occupancy, and arrival headway. And we can notice because this controller not use data fusion technology, so their performance in the low market penetration rate is not that stable. But we can notice that except for the hypothetical scenario in peak hour traffic demand, the other 3 scenarios, the introduction of multi-discrete action space have much more stable performance compared to not use multi-discrete action space in the low market penetration rate scenarios. And for the passenger occupancy, as the passenger occupancy increase, it can grant more priority to buses. But and we can notice that the 10 passenger is a critical point for this scenario in the hypothetical scenarios, and for the real world scenarios, 13 passengers is the critical point. And it also has less adverse impact on the average person delay, which is the green line. And for the arrival headway, just as the single agent scenarios, it is in sensitivity factors. And for the future, there are many works can be done. We plan to first, if we want to further enhance the robustness in mixed traffic environment, we can develop some traffic state prediction components based on the connect vehicle data, and and in this way it can further enhance the performance. And because deep reinforcement learning is algorithm that we call it a black box algorithm. We don't know what action it will be choose in the next step, so it may lead to some disasters. So we can consider to develop hybrid controllers that use baseline control rules as the defense mechanism to avoid that disaster. And also we can in this research we just use the basic deep reinforcement learning algorithms without much refine. So for the future, we can refine the basic model to deal with the complexity of such problems. And we can also consider more comprehensive traffic conditions, such as multi-transit priority requests, and the different stop locations may also matter. And we can also consider oversaturated traffic volumes situations. And another topic can be expand the control object to autonomous vehicles. So we can construct a framework that we control the signal and vehicle together to achieve a better performance. And so this is called single vehicle coupled control. And we can also use different reward function to achieve different expectations. So my work for the isolated intersection has published in two journals. And if you are interested in the details, you can scan the QR code. And thank you. Any questions and comments are welcome.
Great, thank you so much. Very nice, interesting work, and enjoyed the talk so far. So any question? So maybe if you go back while others are warming up to ask question, if you go back to the problem formulation and showing the area, the part that in the reinforcement learning part of the problem formulation, where you had any parameters or anything about the AV penetration rate in that? Was there anything in or communication with autonomous vehicle and signals? Was there anything or no that these were separately being handled?
In this research, we just assume that first we assume all the vehicles in this environment are all connected vehicles, and then we can obtain their data. So we don't investigated their communication details about this topic.
So you assume that all of them are connected,
Yeah.
but some of them are autonomous.
No, we don't consider autonomous vehicles. We just in this research we just consider they are connected vehicle, whether they are but we regardless they are connected or they are autonomous or human-driven vehicle. We didn't consider these differences.
Okay.
We just consider for the connected vehicle we can get the real-time data, and for other vehicles we can't get the real-time data. So that's the differences.
Okay, so could you repeat again this last sentence again? For connected autonomous vehicles, you receive data. For others, you don't, correct?
Yeah, that's right. So that's why in the low market penetration rate, for example, if there's only 20% of vehicles are connected vehicles, so the controller can only perceive those 20%, the data of those 20% vehicle. So their decision only based on those vehicles. So the overall performance is very bad if we don't use the combined states.
Okay, okay. And if you think that adding to this the autonomy, autonomous vehicle, how what part of the algorithm should be modified per person based on your knowledge and insight into the problem formulation?
So if we consider the autonomous vehicle, if we consider we can control the autonomous vehicle, we can formulate the problem. For example, even the single agent, even the isolated intersection, we may formulate it as a multi-agent system for the. So there are two kind of agents. Such as the controller is an agent and the autonomous vehicles are also agents, and then we can use multi-agent reinforcement learning to solve that problem, and it may have better performance because we can adjust the speed and of the autonomous vehicle, and in this way we can control the phases and their traffic flow simultaneously. I think they can be achieve better performance compared to the framework I used in this research.
Okay, good. Thank you.
You're welcome.
So, any question from the audience? Dr. Fan, any other difficult question that was left from the PhD that you would like to ask now? You're mute, by the way, if you're asking that question. Okay. So, yep, you can now unmute yourself.
Yeah,
Daniel.
I can unmute now. So
Yeah.
he has been doing great. He published 2 papers, as you can see from his
Oh, yep. Yep.
He's based on what I heard, he's doing great right now in Penn State as well.
Oh, yeah, of course.
Yeah, thanks.
Yep. Yep. Thank you.
This is Daniel. I have a question. Can you talk more about the data you got from Charlotte? Was that just the model representation of the intersection, or did you get like actual recordings of flow through the traffic intersection? Could you repeat on that a bit?
So for this data, I just emailed to Charlotte DOT, and they provide the data for the intersection I request for. So for this traffic volume data, they give me tables with each row corresponding to different time, and also the counts of each turning movement. So this is the table format, the data format.
And do you know how they got that data? Was it through camera, or did they use like loop detectors in the ground to determine direction?
So I didn't know because I didn't quite focus on this point, and I think you can just write email to ask them.
Okay, yeah, thank you.
You're welcome.
So, any other question? Great. So if not, let's thanks again the speaker for today's. It was very interesting talk, and we enjoyed it. And also thanks everyone who joined today's event, and wish everybody a great weekend.
Thank you.
Thank you.